everybody. So this is a video for experiment 11 from Chem 110. So this is molecular modeling. So this is a two-part experiment. So the first part actually has you guys work with some molecular modeling kits, which are a very common way to look at molecules in 3 dimensions. So we're going to do a little bit of that right now. The second part is you guys doing some molecular modeling computationally through SciGrass. So you guys will do that on your own. Okay, so the model kit that I have is a very simple one. It's one that you guys would have used in lab. So as mentioned in your lab manual, there are different pegs which represent atomic centers. So let's see if we can find one here. So I have a peg right here. This has 4 little pegs surrounding the atomic center. So you would use this for something that has 4 electron groups around it. Total. So to make our models, so we're going to make methane first. So methane is CH4, it has carbon surrounded by 4 hydrogens that are singly bonded to the carbon. It's shown in the picture in your procedure. So to make our bonds, we use these green straws, like this. So the green straws are actually represent the bonds here. So we have single bonds, so we're just simply going to put a green straw on each of these little pegs. So those will represent the 4 single bonds. Okay, so now we have our carbon in the center with our 4 single bonds, and then we will put a hydrogen on the end. So for hydrogen, I'm using these pieces that only have 1 peg. When I'm done making this, okay, so now you see here's our methane. So you see that the picture, although it appears flat, methane is definitely not a flat molecule. It has a tetrahedral shape around the carbon atom. So each of these hydrogens point to the vertice of a tetrahedron, or corner of a tetrahedron. Okay, so that's methane. Now to build ethane, ethane is C2H6. So that means we need to take this carbon atom and bond it to another carbon atom. So what I'm going to do, so I'm going to take one of these hydrogens away, and I'm going to find another carbon, so another 4-pegged carbon, because you'll see that there are 4 electron groups around carbon and ethane. So I'm going to put in the second carbon, and then I'll need 3 more straws. And 3 more hydrogens. All right, so that's simple turn a 1 carbon molecule into a 2 carbon molecule. So this is ethane. So both of those carbons are tetrahedral. And one thing you can see is that you can see in a model kit that you're not going to be able to see on a piece of paper is that there is actually, you can rotate around single bonds. So I'm changing, we call these different conformations. So I can have a conformation where all the hydrogens line up with one another, or I can have one where the hydrogens line up in between the other hydrogens, so something like this. Okay, so you're going to learn more about that when you take organic chemistry, but there is what we call free rotation around single bonds. Okay, so that's ethane, and you can make more complicated molecules, so we're going to look at two of those. So here is our first one. This is butane. So it's basically taking this and adding 2 more carbons and some more hydrogens on. So butane is C4H10. And it looks like I lost a hydrogen here. Get it out. Okay. So here's our butane. Much bigger than our ethane, about twice as big. And once again, you can see that around any of these single bonds, I can rotate the molecule. So rotate around that bond. I can rotate around the central carbon-carbon bond here. And I can also rotate on this one end. Okay, so you get many, many more different conformations for butane. You can see around each butane has about this, every carbon in butane there's the same geometry. Take a guess of what that is. Oh, we're losing hydrogens. Not good. Okay. So some of these straws are a little bit loose on the end, so some of the atoms fall off. Okay, so that's butane. Let's take another one. So you can also have molecules that have cycles or cyclic pieces. So you can have atoms joined in a ring. And one of the more common and most interesting ones is cyclohexane. So this is 6 carbon atoms. Well, let me look at that. 6 carbon atoms that are in a ring, and each carbon has 2 hydrogens, so that's C6H12. Okay, and right now I have the cyclohexane in what we call the chair conformation. And this conformation, it's a little hard to see, but you can, if you examine it, if you look down a carbon-carbon bond here, the hydrogens are actually all in between the hydrogens on the atoms that are next to it. And that's a very low energy conformation. So just like with the other molecules we looked at with single bonds, when you have cyclic molecules, they can also have different conformations. So I'm going to twist this around. And here's another conformation. This is the highest energy conformation of cyclohexane. We call this the boat conformation. Here's our boat conformation. And one thing you can see that's different here is that you do have some carbon hydrogens along, for adjacent carbons that are lining up with one another. So that makes the energy higher. And then if you look here on these 2 central atoms, you have these hydrogens sort of facing one another, and that is also unfavorable. We call these steric interactions. So this is pretty unstable. This is an unstable conformation of cyclohexane. Cyclohexane also has another conformation called the twist boat, which is a little bit more complicated, but you can see that you can actually rotate and twist the atoms into different conformations. Okay, so single bonds in that way are pretty flexible. There are different conformations around them, breaking molecules again. Okay, so now let's look at some molecules that have multiple bonding, so double bonds mostly. So we're going to build ethene, and with this model kit, the way that you build ethene is if you look at the Lewis structure for ethene, there are 3 electron groups around the carbon. There are 2 single bonds and there is a double bond. So I want to find an atomic center, carbon, that has 3 pegs. Let's see what we have in here. I need to go through a different color. Alright, so we can use this for one of our carbons. It's a 3 peg piece, but now there's a hole in the middle. Okay, that's going to help us to make our multiple bond. So let me try to find a second one. Here's another one. So we got 2. Okay, and I'm going to join them together with a single straw. Okay, so that's one of my bonds, and then I can put some more straws on here. Actually, before we do that, let's make the double bond. So this is the 2 carbons with the single bond. Now to make the double bond, we have these other pieces. So these pieces here, they're clear, kind of white, clearish color. And there's one peg that we can use to put our straw on for the bond. But you can see there's another little peg here. So what we're going to do with that is we're going to take that and snap it into the hole in the middle of this one carbon piece. So now what I can do is I can put a second straw on there. And now I can make my double bond. And then I'll put my second clear piece on and snap it into the other hole. So now I have 2 atoms, 2 carbon atoms, that if you look sideways at it, there's now a double bond there. So that's how we use this kit to make double bonds. And so I can put some more straws on here. Try to keep the straws the same size, but it's kind of hard sometimes. Okay, let's see if we can find one that's the same size. Okay, there we go. There's our hydrogen bonds, almost the same size. We'll just run with that. Okay, so here's our ethene. Now you might want to ask, can I rotate around the double bond like I can rotate around a single bond? And the answer is actually no, I can't. I mean, I can try, but if I try to rotate it all the way around, I'm going to end up breaking the bonds in the middle. And that's actually what happens if you want to rotate around a double bond. You're going to have to break the pi bond that's part of the double bond. And that's going to take a lot more energy than rotating around a single bond. So we get different conformations of molecules with double bonds because, like cis-trans isomers, because you can't really rotate around a double bond as easily. So it's not as flexible. Okay, so let's look at another molecule that has double bonds in it that I pre-built. And this is C4H6. This is 1,3-butadiene. Okay, so it's like butane, except now we have alternating, there's 4 carbons, 1, 2, 3, 4. But if I kind of tilt it sideways, you can see that there are double bonds between these 2 carbons here on each of the ends. So if I try to rotate around those bonds, I can't. It's pretty rigid. Actually, it is pretty rigid because I think the straws are not quite the same size there. So that's pretty rigid. If I want to rotate all the way around, I'm going to end up breaking that double bond. But there is a single bond in the middle. And theoretically, I should be able to rotate around that, and I can. So you can get two different conformations. So this is your trans, just kind of the carbons are zigzagged like this. And that is cis. And one thing you can kind of see here is that this molecule is flat. So is ethene. So here's ethene, that's also flat. This is pretty flat. You don't get a conformation like that. It's kind of advanced bonding, but so there is your C4H6 molecule. So you can rotate around that single bond, but you can't rotate around any of the double bonds. Okay, so you can build molecules that have ring structures or cyclic pieces with double bonds too. And probably the most famous common one is this guy here. This is benzene, which is C6H6. And if you look, I have alternating double and single bonds, just like in the butadiene case, except this is, everything's in a ring now, so there's 6 carbons in a ring. The ring is kind of hard because I think some of the straws are not the same size. It's kind of hard to get them all be the same size. But benzene's flat. And we had cyclohexane here, which also is a ring of 6 molecules, but because you have all single bonds, this is definitely not flat. You definitely have a nice, robust 3-dimensional geometry there. But here, this is flat. Okay, and not flexible. So I can't rotate. It's even less flexible than not having the ring. I can't rotate at all around any of those bonds. Okay, so we saw some simple, some complex. Now let's look at 2 other samples of some macrostructures. So I'm going to move that back there. So I have 2 models for you. So this model here is diamond. You can probably do a Google search and get another good picture of diamond, but this is diamond. Okay. If we look at each carbon, it's an allotrope of carbon, different form of carbon. So diamond has, if you look at each carbon here is bonded to 4 other carbon atoms. And you're going to have to compare this to one of the smaller structures that we did. So here's cyclohexane. You might want to kind of compare to that. Or you can compare it to benzene. You have to decide which one is it most like. So that's diamond. That's one allotrope of carbon. The other allotrope of carbon we're going to look at is graphite. And here is one sheet of graphite. There's one sheet of graphite there. And if I tilt it this way, you can see that the structure is pretty flat. And if you look at each carbon here, so here's a carbon in the middle. Now each carbon is bonded to 3 other atoms. And no matter which carbon you look at, sort of in the interior, this extends outward more. Each atom you look at, there's 2 single bonds and a double bond for each carbon. Here's another carbon, 1 triple bond, 1 double bond, and 2 single bonds. Okay, and if you look at your double bonds, they're sort of alternating here. We call conjugation. So there's a double bond, I keep saying triple bond. There's a double bond, single bond, double bond, single bond. Okay. And so again, you have to figure out, what is this most like? So here we go again. So here's cyclohexane. Is it like cyclohexane? Or is it like benzene? That might be a little too easy. There we go. That's benzene and a sheet of graphene. Now, what you should realize about graphite is that this is one sheet of graphite. Or what we call graphene. Graphite is actually made of several sheets. So here's another piece of graphite, and they actually sit on top of one another, kind of like this. So that might help you on one of the questions. That's sort of what graphite looks like. It's multiple sheets like this. They all stack on one another, and they're pretty far away from each other. The sheets are not bonded to one another. Okay. So that is part 1. So you guys are ready to go do that part of your lab report. So have fun with that. Stay safe and stay healthy, and held a pit.